Thanks everyone for coming to this talk, and thanks to the organizers for organizing QCrypt given these circumstances. I'm Ian George. I'm going to talk about some joint work with Gia Lin and Norbert Lutkenhaus on numerical calculations of finite key rate for general quantum key distribution protocols. So let's get started. The motivation is pretty straightforward. People are now trying to implement quantum key distribution protocols for industry use. I know we all know what quantum key distribution is, but just as a quick reminder, it's a two-party quantum cryptographic protocol in which Alice and Bob share a quantum channel, an authenticated classical channel, and using these resources, they want to establish a secret key. So what's the issue? The issue is that now that we implement these things in real life, we need to be able to handle side channels and practical issues in implementations with respect to finite size behavior. We need to do this because in real life we have a finite number of resources, and so we need to be able to handle the finite size with these other practical issues. So the problem is that to determine type finite key using analytic methods, you need certain symmetries. However, most QKD protocols lack these symmetries either inherently or because when you implement them in real life, some problem with the actual implementation destroys these perfect symmetries. Our solution is a numerical method that doesn't need these symmetries. It uses Renner's framework for finite size effects, and it extends the numerical method for tight asymptotic key rates to the finite regime. So the rest of this talk can be divided into three parts. The first one is the finite size framework of Renner and an improvement presented in our work. Then the extension of the numerical method for asymptotic key to finite size in this framework. And lastly, we consider examples of our numerical method to see its generality and its practicality. So let's start with the finite size framework. In a general device-dependent QKD protocol, one can divide it into 7 steps. Here we'll talk as if it's entanglement-based, because without loss of generality, one can always convert a prepare and measure QKD protocol into an entanglement-based one, using source replacement. In the first step, Alice and Bob receive their signals. In the second step, they measure their signals and record the outcomes, partitioning them into public and private information. Public they'll announce later, private they will keep throughout the protocol. In the parameter estimation step, they check how correlated their signals are by announcing the outcomes for some subset of the measurements and constructing a joint frequency distribution. If they appear to be sufficiently correlated, they continue, otherwise they abort the protocol. They then make announcements and perform general sifting to remove any data that they expect a priori to be poorly correlated. Then Alice performs a key map to construct the raw key. To do this, she uses her original outcomes. Then they perform error correction, which allows Bob to guess Alice's raw key. And finally, they perform privacy amplification, which shortens the raw key to some smaller size, but in exchange decouples them from Eve. So the major finite size effect that we have to consider is during the parameter estimation protocol. A parameter estimation subprotocol can be viewed as a CPTNI map that takes in M states and outputs either abort or pass given that measurement. So visually, you can see the state row AB that's being fed into the Alice and Bob's respective measurement devices, and then using classical communication, they construct some frequency distribution F. If it is in some pre-agreed set Q, then they'll continue, otherwise they abort the protocol. One can therefore view the parameter sub-protocol map as determining the probability that they're going to pass, given that the input was rho. We also need this notion of coarse-grained data. So if you think of the data that is constructed just from the outputs of their respective POVMs, then you get what is fine-grained data. You consider it fine-grained because it's the most information in some sense one could possibly extract from the protocol given the design of the protocol. However, one can also consider coarse-grained data, which is mapping the fine-grained data to some smaller set of outcomes. For example, in BB84, while there are 16 outcomes for fine-grained data, coarse-grained data, you could consider things like phase error, where there's only 2 outcomes. So we also need the notion of epsilon securely filtered states. The reason for this is if you think about having a finite number of tests, then you'll never truly know what state you're sampling from. For example, you could consider the maximally mixed state and measure it a series of times and still get the statistics that the state that you're sampling from is the maximally entangled state. Of course, this happens with low probability, and so the intuition is that you should throw out all input states, which, except for with very low probability, you would abort on anyways. So visually, you could imagine any arbitrary state rho, you feed it into your n measurements, you use m of them to construct your frequency distribution f, and then you either abort or pass. It follows that we want to consider the set of epsilon securely filtered states so that we may ignore them. The intuition for this would be, for example, the maximally mixed state previously discussed would lead to a zero key rate. However, we want to be able to establish a positive key rate in the finite regime. Therefore, we need to throw out these states. And we expect that this will come at low cost because we're saying that they will rarely occur. To determine this set of states, we need some structure of our protocol. In the case of device-dependent QKD, we have the joint POVM gamma tilde j, the fact that at the end of the parameter estimation subprotocol, they will obtain some statistics f, and we know that they have some pre-agreed upon set q, which will determine whether or not they abort given the statistics f. So, using this structure, under the assumption of collective attack or equivalently IID input to the parameter estimation subprotocol, by the use of law of large numbers, one can construct the set S mu, which only excludes states which are epsilon securely filtered. The intuition for this is that this map phi p is the joint measurement channel between Alice and Bob, and so it determines the probability distribution of Alice and Bob's joint outcomes. Therefore, you then just check if there's a probability that there's a frequency that you would accept upon within some distance of that state, and if so, then you need to consider that state. Therefore, it is a question of the distance between the probability distribution of the measurement and the frequency distributions that you would accept on within some value mu. However, there is an issue. This set is not optimal because of this choice of mu. There are a couple ways to see this. The first one is, instead of using the law of large numbers, if you have a two-outcome POVM, you could just tighten mu by using the Hoeffding inequality instead. Perhaps more fundamentally, it suggests that coarse graining can improve the finite key rate in some cases. The reason for this is because this value mu depends on sigma, which is the number of outcomes of your joint POVM. And so if you coarse grain, for example, in BB84, from 16 outcomes to just phase error, which either there is a phase error or there isn't, then you can significantly tighten the value of mu, therefore improving the key rate. This is a problem because it suggests that coarse graining, which is like throwing out information, helps Alice and Bob be more secure from Eve. So is this true? Of course not, and that's what we show. The intuition for this is as follows. Given the protocol, you have some measurement channel phi p, and then you have two coarse grainings M1 and N2. You're only going to accept on some frequency distribution q, and so under the coarse graining, you could just imagine that they're accepting on FC2 or FC1. Because N1 and N2, that is the coarse grainings, have different numbers of outcomes, mu1 differs from mu2, which is why the sizes of the sets of probability distributions to be considered differ in the two cases. In some cases, as we will see in the examples, under different coarse grainings, the set of states which would map into those probability distributions differ. Therefore, by taking the intersection, you consider a smaller set of density matrices than if you considered either of them. The idea, though, is that both of them are excluding the same epsilon securely filtered states. You're just using the same fine-grained data with different coarse grainings, and so you should be allowed to consider the intersections. More formally, the idea is this. Given a QKD protocol with some acceptable observations Q, you could consider k coarse grainings, each with their own respective variational bound and each with their given number of outcomes lambda k. For each of these cases, you could construct the set S mu k, which is the same as what we discussed before, other than we've added the coarse graining in the trace norm, and we've replaced mu with mu k for the respective k. In this case, each set is going to only throw out epsilon securely filtered states, and so by taking the intersection of them, you're only excluding epsilon securely filtered states. Therefore, your key rate can only go up, and your security parameter stays the same. Having gone through the finite size framework and our improvement on it, we now focus on the extension of the numerical method from the asymptotic regime to our finite size using this framework. The asymptotic key rate is given by the Dev-Attack-Winter formula, where the first term has to do with the privacy amplification and the second term has to do with the error correction. This error correction term can be determined experimentally, and so the algorithm focuses on the minimization term. The reason it is a minimization term is that even asymptotically, multiple states may produce the same observations, and therefore one must minimize over them. The conditional von Neumann entropy is evaluated on the processing of rho given the QKD protocol. The algorithm starts with some guess of the optimal attack rho naught and then converges to the optimal attack rho star. At some stopping condition, it takes the linearization about the current result rho and then computes the dual and finds the lower bound by going to the boundary of the set S. This means that we always determine a lower bound of the key rate. Furthermore, in the case where the algorithm achieves rho star, then by taking the linearization about that point in the dual, one still obtains the optimal answer, which is to say the method is tight. In the finite regime, it's a very similar idea. In this case, we have these failure probabilities epsilon, but we're mostly concerned with calculating this term L. In this case, we still have a privacy amplification term, but it's now called h mu, and the difference is that it will now be a minimization over the set S epsilon PE discussed earlier, rather than over the set S. We also have the terms leak epsilon EC and this delta. The leak epsilon EC is just the error correction term with some finite size fluctuation cost, and the delta epsilon is another finite size fluctuation cost. Therefore, our numerical algorithm can still focus on h mu. Just as in the asymptotic case, one can write the optimization problem as a semi-definite program. The source replacement constraints pertain to lifting prepare and measure protocols to entanglement-based protocols. The statistical fluctuations are described earlier, and the acceptance set Q is a specific assumption for how it should be constructed so that it can be written as a semi-definite program. However, the acceptance set Q's assumption is not unreasonable. It handles any sort of case in which you would start with some ideal observations and allow any observation within some distance from it under the trace norm. This is natural, for example, when one thinks of BB84, as one might expect that they want to accept phase error statistics of 2% or less, and this would handle that exactly. Lastly, we must make sure that our numerical method can handle coherent attack analysis, as coherent attacks are the strongest attacks available to Eve in the finite regime. Here we consider two ways that we can handle it with our numerical method. The first is the finite quantum D-Finetti theorem, which all it does in terms of the solver is increase the size of variational distance mu, which one can program into the solver before running it, and add some correction terms which one can subtract off. Second, one could use the post-selection technique, which says that the epsilon security on coherent attack is polynomial in the epsilon security of collective attack. It follows that one could just divide the epsilon security of the collective attack by the polynomial term that we're interested in, and then calculate the collective attack in that to determine the coherent attack. So the takeaway is that our solver can handle both coherent and collective attack analysis. As all of our examples will be presented using IID collective attack, it's important to quickly go over the difference between the results for that and the results for coherent attack analysis. Therefore, we'll present the simple BB84 for these different cases. So here we have the IID collective attack. Now we have the quantum D-Finetti theorem. As one can see, there's this jaggedness, but that just has to do with the fact there's an extra parameter one has to optimize over, and I discretely optimized over it. One could improve the result somewhat, but not in the low signal regime by optimizing more carefully. And lastly, we have the post-selection technique, which one can see does significantly better than the quantum D-Finetti theorem. So having now explained the extension of the numerical method to the finite size, we're now going to consider examples of our numerical method to look at its generality and its practicality. Of course, whenever one has developed a new numerical tool, one wants to make sure that it can at least do as well as the analytic tool when it's available. And so that's what we're doing here. You can look at the simple BB84 that's presented in the Skorany-Renner case. The lines are the theoretical results and the dots are numerics. And what we see is that our numerical dots are right on the theoretical line, which tells us here we do just as well as the analytic result. So we now want to think about a protocol which the numerical method could do better than the analytic method. So if you think about BB84, Alice sends these 4 states to Bob, the 4 states being the 4 green dots on the block sphere. So imagine that she sends them to Bob, but through the channel they get rotated about the y-axis by some amount. And so it's sort of like Bob's reference frame is misaligned because it's sort of like he's been sent this rotated block sphere. And so Alice and Bob no longer agree on the z and x axes, and therefore their reference frames are misaligned. Hence we call it reference frame misaligned BB84. However, because of this specific rotation and the measurements that are used in BB84, sufficient tomography should allow them to determine this rotation, and so he should be able to undo it using sufficient parameter estimation. And since it's a simple unitary, this shouldn't affect the key rate. So that's the idea, and we're going to look at this a little more. So if you think about the case where there is no unitary rotation and the noise model is very simple, there's equal phase error and bit error, then the joint probability distribution table between Alice and Bob is as below. The numbers are for the 2% qubit error rate. And you can see that there's really nothing to gain by not coarse graining. That is to say, you might as well just check what the phase error and bit error are, which are on these pink blocks. However, in the rotated case, there's a further nuance. So here we see the joint probability distribution table in the case of the rotation and the error. And one can see that the bit and phase error terms have increased. But furthermore, there's this asymmetry in the off-diagonal blocks. And so the idea here is basically that if you were to coarse grain the data, your phase error would go up. But if you were to consider the fine-grained data, because you should be able to notice this asymmetry, you could sort of detect the unitary and then undo it. And so that part of the phase error would go away. And so at least asymptotically, you would expect that the fine-grained data should do better than the coarse-grained data. And so we're now going to look at that numerically. So here we see the phase error and the fine-grained statistics key rates as a function of the number of signals sent. And what we see is that in the small signal limit, the phase error does better than the fine-grained statistics. And that just has to do with this thing we discussed at the beginning of the talk, where the variational bound mu depends on the number of outcomes. And so the phase error does better because this variational bound mu is smaller, and so the number of states that you have to optimize over is less, so your key rate goes up. However, in the large signal limit, we see that the fine-grained statistics does better, and this is because it can detect this unitary that we were just talking about and undo it, so it gets a better asymptotic key rate. And so it looks like there seems to be this trade-off between like undoing these sort of effects and considering the coarse graining so that you get a better key rate in the small signal limit. But of course we had this whole point that we could optimize over multiple coarse grainings at once. And so if we consider both the phase and the full statistics at the same time, what we see is we get the best key rate in all regimes. And so this is actually, in some sense, one of the major powers of our numerical solver is its ability to handle multiple coarse grainings, which would be very difficult analytically, and yet in some cases gets you significantly better key rates. So we also should look at what other sorts of protocols it can handle. So it can handle MDI QKD protocols. This is sort of intuitive in the sense that if you think about it, what an MDI QKD protocol is basically doing, it's just you're now going to do parameter estimation over a tripartite joint probability distribution because Alice, Bob, and Charlie all have outcomes. And so this, of course, fits within the numerical framework, and so it works. Lastly, as our final type of protocol we're interested in, of course, optical implementations of QKD protocols are very nice. They do have this problem that often they can't be represented in finite Hilbert spaces because light is in an infinite Hilbert space. However, in the case where there exists a squashing model which allows us to represent it in finite dimensions, we can use our numerical method for the finite key in that case too. So here we consider the discrete phase randomized BB84, where the idea is just Alice is going to discretely randomize the global phase of her states as she sends them to Bob. And so here we consider just one discrete phase, which is sort of like optical implementation of BB84, and then also two discrete phases, which should improve the key rate as it allows one to detect Eve better. And so we see that it requires quite a number of signals, and really what this has to do with is that you need enough signals to get your set tight enough with respect to the loss in the channel. And this can be sort of better seen by if you increase the distance, which is to say we're going from 20 kilometers to 100 kilometers, then the loss in the channel goes up, and so the number of signals necessary to get a positive key rate also goes up. Lastly, we want to talk about practical acceptance sets Q. So the intuition behind this is, in all the previous examples, we've sort of implicitly assumed that Alice and Bob are only accepting on one frequency distribution, all the others they'll abort on. And this is a common thing people do in the finite key analysis papers, but you really shouldn't do it in general, and it's pretty straightforward. Why? If you think about having a finite number of tests, then there should be some variation in your frequency distributions when you run the protocol each time. And so you want an acceptance set Q that has enough frequency distributions that you'll frequently accept your protocol, at least on honest implementations, even within these fluctuations. But so then the question becomes, okay, so in what cases does using the numerics help? And so in the simple symmetric BB84 that we discussed earlier, you kind of see that it shouldn't help, and the reason for that is, well, you just know that the worst case scenario within your acceptance set Q is the worst phase error that you'll accept. And so this is sort of numerically seen in this graph, because here we consider, we optimize over the set Q with this symmetric observations, and as such, including the phase and the fine-grained statistics together doesn't improve over the phase statistics. And so it's the same sort of idea. If you can predict that the phase statistics is sufficient, you can also predict what the worst case scenario within your observations will be. However, in the rotated case, it makes a significant difference, because in this case we don't know what the worst case scenario observation within the set will be. And furthermore, we'll need this multiple coarse graining to get the optimal key rate. And so this sort of opens up the ability to look at, like, okay, if your protocol is implemented and something goes wrong to some degree, we can now use our numerical methods to see if we can still get a decent key rate out of it, even if we don't know what the worst attack is or something, which is another major advantage of our numerical method. So to summarize, in this work we improved the analysis of the parameter estimation sub-protocol in that we can now optimize over multiple coarse grainings. We constructed a generic numerical solver for determining the finite key rate of QKD protocols represented in finite dimensional Hilbert spaces, where the generality is both in the types of protocols that can be handled and its practicality. And lastly, we considered when our improved parameter estimation analysis may be advantageous using our numerics, and hopefully in the future we could use this to investigate side channels in the finite regime. Thank you.